and get dizzy for a moment. Alright, so the game of life is based on some work that John von Neumann did back in the 1940s, and then was really taken further by Conway, I think around 1970. And a lot of people would write very simple programs to try to simulate something like this. So what he was looking for was a set of simple rules that could lead to very interesting behavior. And so the big part of this course is leading up to the parallel project. And so this is a really good way to introduce parallel computing, some of the issues and some of the questions of what can you see. Now, when we're building the Superstar Destroyer, I hope it's pretty clear what we're going to see. I'm expecting to see something that looks a lot like a Superstar Destroyer. You somehow build a Millennium Falcon, I think that would be fascinating with the pieces you're given, but that's not the kind of behavior I want to see emerge. So we have something very structured. So the game of life has a couple of very simple rules. So imagine you have a grid of squares. All the squares have the same lengths, so each square is going to have 4 neighbors that connect to it on sides. We're not going to consider diagonal connections. And so the rules are the following. Any live cell, so that's going to be a cell that's filled in, with fewer than 2 live neighbors dies, as if caused by underpopulation, boredom, however you want to phrase it. You've got to be in a populous group to keep living. Okay? The next one is any live cell with 2 or 3 live neighbors gives birth, lives on to the next generation. Okay, so are these two consistent? If you have fewer than 2 live neighbors, you die. If you have 2 or 3 live neighbors, you move on to the next generation. What are you wondering about? Yeah, what if you have 4 live neighbors? What happens?
You die.
So the next one is any live cell with more than 3 live neighbors dies as if by overcrowding. So over here, I'm not thrilled with that phrasing. If you have 4 neighbors, do you also have 3 neighbors? Yes. And so I don't think that this is the best phrasing. Maybe I'll be inspired to actually go to Wikipedia and edit it, but I'm just worried as to where this is coming from. So if you have 4 neighbors, you die from overcrowding. That kind of makes sense. Too many people competing for the same resources. And the last one is any dead cell with exactly 3 live neighbors becomes a live cell. So basically, this is how birth happens. Okay? If it wasn't for 4, this would be a very boring game. Right? What would happen if there wasn't condition 4?
Everything would die off.
Steady.
It's not clear everything would die off.
It reaches a stable point.
It would reach a stable point. So the first question is, can you have, if there's no birth, can you have a configuration where it just survives forever? So what would be that configuration?
4 squares.
4 squares next to each other, forming the super square. That would survive forever. So it is possible to have some systems that will propagate for all eternity. But without 4, however many cells you start off with live, then in the future you're never going to get anything more than that. Cells can only die, so you'll have some kind of limiting process, and it'll be a subset of the initial configuration. Because of property 4, very interesting dynamics can happen. And so when Conway wrote the paper, he posed a $50 question. You have 1 year to solve this. Is it possible to create an initial configuration that will lead to an unbounded growth in population? Or does the population have to stay finite? It could be a very large finite number from the initial configuration, but will it stay bounded? If you have heard of Mathematica, the founder of Mathematica, Stephen Wolfram, has done a lot of stuff in cellular automata theory. This has been used to model a huge variety of things in the real world. So I'm just trying to show you a little bit of what's out there mathematically. This is a great topic to look at. A lot of research is being done in this. It turns out this is equivalent to Turing computers. In terms of what you can do with a Turing computer, you can do with this. You can compute a lot of stuff with such systems. And again, what a lot of people like about these is you have 4 very simple conditions. So the question is, how do you propagate, how do you calculate how the system propagates in time? Well, one thing is to just go through line by line by line for each cell, look at its neighbors, and then decide what happens at the next moment. Well, we talked a little bit about how this could be parallelized. Each cell could be assigned a different computer or a different processor. The difficulty is when you're doing something like this, you have to be able to keep track of common memory. And they have to be able to call things from memory. The more memory calls you have, the more expensive things are. So the question is, how do you manage the information that the different parts need? You can break your region into subregions and have each one analyzed by a different computer. What's the problem with something like that? So I take and I break it up into 4 giant subregions, and I have 4 computers each.
Like what happens on the boundaries between the regions? So
what happens on the boundaries between the regions? So you can parallelize it into big blocks, but then at the end you have to figure out, well, what's happening on the interface. So this is an extremely parallelizable problem. So if you want things to go quickly, this is a great thing. How many of you have played computer games? How many of you have hacked computer games? So I think it's more fun hacking than playing them. Okay. Somebody tell me a popular computer game you've played. Sorry, your hand up.
Minecraft.
Minecraft. Okay. What happens in Minecraft?
Well, you have a bunch of blocks of different types, and you interact with them in one way or another. You can place them, destroy them, create new ones based on the ones that you collected.
Okay. And how are these? Okay, other games people play. Only Minecraft.
Skyrim.
Okay, how do you play that?
You delve into caves, or dungeons, and
Okay.
get weapons and armor and fight enemies and fight dragons.
Do you ever see trees, rocks?
Yes, lots of trees and rocks.
How do you think the trees and rocks are placed?
Using a random algorithm?
It's interesting, they use pseudo-random algorithms that run very fast and are very deterministic. So the trees are often not placed entirely at random, but they're placed in a way that looks pretty random. And so for a lot of these computer games, they want things that can process fast. So if you're interested, in computer games and stuff like this, look up how they actually choose where to put the images at times. And so again, you want to break things up so that you can compute quickly. For stuff like this, it's entirely deterministic. Once I give you the initial configuration, how the system evolves in time is completely determined. Now the problem is, if I give you a 10 by 10 grid, how many initial configurations are there? So 10 by 10 grid.
10 to the 10.
Not 10 to the 10. 2 to the 100. Each cell is either live or dead. I have 100 cells, so I have 2 to the 100 initial configurations. In computer science, you learn that 2 to the 10 is actually 1024. So if you talk about megabytes and gigabytes, it's bad use of the notation. A megabyte to a gigabyte, it's supposed to be an order of 1,000. But in computer science, it's actually 1,024, because 2 to the 10 is 1,024. So if you have 2 to the 100, that's 2 to the 10th to the 10th. That's 1,000 to the 10th. 1,000 is 10 cubed, so we're talking about 10 to the 30th. So we're talking about roughly a little bit more than 10 to the 30 initial configurations. So when Conway asked this question of, will you find a pattern that has, growth going off to infinity? If you even want to just confine your initial searching to a 10 by 10 grid, there's 2 to the 30th initial configurations. That's far more than you can calculate or look at. And so it became a really daunting problem. How do you intelligently search among spaces like this? And so you can see when you're doing these searches, you want to calculate things as fast as possible. Savings of a factor of 2, 10, 100 can really speed up the size of the grids you can look at. And so I thought I would show you some of the successes people found in this problem, because they're somewhat interesting. So the first, it was done within the years, the plasma sliding gun. So if you notice over here, these 2 squares, these are the initial configurations that we said would survive forever. I can't remember if this has cheesy music or not. No, this does not have cheesy music. So the things are going back and forth, and what you can see is when they meet and they interact, they end up creating a little glider that's launched. And so as time evolves, it just creates more and more gliders going off to infinity. So this resolves Conway's initial problem. Okay? Here's an initial configuration of the game of life, and now it speeds up a little bit, that just keeps creating more and more gliders. Okay. It's always interesting what they then show you should look at next. Do you consider this a solution to Conway's initial problem? Yes or no? This is an easy question. Yes, right? You created something that goes off to infinity. It's a very special going off to infinity, just one straight path. So the question becomes, can you create more interesting things? And if you are interested, there's a lot of interesting work in this field. So here is the Game of Life breeder. So this is a far more complicated configuration. So this is going off to infinity, and as it goes off to infinity, it creates little glider guns in its wake. And so just the thought of how people would construct something like this, to me has always been fascinating. Okay. So that's basically, the first piece of mathematics I wanted to discuss today. Something very simple like the Game of Life, very basic rules, can lead to extremely complicated behavior. But again, it's completely deterministic. So you give me an initial configuration. With enough computing power, I can figure out what's going to happen. But the question is, how do we get that computing power? And this is where parallel computing comes in. So again, I want you to just get second nature. Whenever you see a problem, can you parallelize it? All right, this next problem I want to talk about is Pascal's triangle. So we talked about Pascal's triangle, I think, on the first day of class. This is the 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. Keep going down like this. How many of you have not seen Pascal's triangle before? Okay. Because I'm lazy, when I programmed it in Mathematica, I did Pascal's triangle not as like an equilateral triangle, but as a right triangle. It just made it a little bit easier to write the code. My 6-year-old son didn't really seem to mind, so it was acceptable. How many of you have looked at Pascal's triangle modulo 2? Okay. So how many people do not know what the phrase modulo 2 means? Okay. Modulo 2 means I take my integer, and if the integer is odd, I replace it with 1. If it's even, I replace it with 0. I basically look at its remainder when I divide by 2. Why might this be an interesting thing to do? So what do we know about Pascal's triangle? How do you get one row
Relates the coefficients of binomials.
Okay, so one of the reasons we care about Pascal's triangle is the coefficients are related to what happens when we expand x plus y to the end, the binomial theorem.
Each entry is the addition of the two above it.
Okay, each entry is the addition of the two above it. So let's think about how addition works modulo 2. What's even plus even? 0. So in fact, we can do even plus even equals even. Okay, what else? Even plus odd
equals odd.
Odd plus even.
Odd.
And last and least, odd plus odd. So when we're trying to figure out Pascal's triangle, we essentially inherit from the previous level. If we have two even numbers, this sum is going to be an even number. If we have two odd numbers, we have an odd number. The key relationship for Pascal's triangle holds mod 2. Now what do you think you should do after we study Pascal's triangle mod 2? Mod 3. Mod 4, mod 5. Maybe mod 4 is different than mod 3 or mod 5. Why might mod 4 be different?
It's not prime.
It's not prime. Maybe it doesn't matter. Maybe it matters how a number factors. So I'm only going to look at Pascal's triangle mod 2. I urge you, if you like problems like this, to look at other moduli for Pascal's triangle. And then the question that I want to deal with for you guys is, how do you construct this triangle well? So I'm going to show you some code I did, and we'll talk a little bit about how you might actually write this code. Alright, so I have loaded all the files in. Okay, so I'm going to start running a movie in Mathematica. Every time I have a number that is odd, I'm going to put in a blue dot. If it's even, I'm going to put in a white dot. Okay? So here's the movie. So at first it's a little hard to see. Now the dots are slowly beginning to appear. Okay. And so what's happening is each column is another row of Pascal's triangle. I'm just doing it as a right triangle. When you think you start to see a pattern emerging, let me know. All right. So let me try to stop it. Okay, so what kind of pattern do you see emerging?
Sierpinski triangle.
It's a Sierpinski triangle. So this is a fractal geometry shape. So again, if you're interested in stuff like this, read about Sierpinski triangles. These are figures that are very self-similar. And so I'm going to basically keep getting copies of it. So if you look over here, this region over here looks a lot like the region over here and the region over here. Fractal geometry is used in a lot of movies to make things look very realistic. I think the first movie that used it was one of my favorites, Star Trek II, The Wrath of Khan, when they were doing the Genesis torpedo, and you're seeing how it terraformed the planet or the moon. That was using fractal geometry for the landscapes to make the coastlines look reasonable. So what I'll do now is I'll run it a little bit more. So this is at 34 levels of Pascal's triangle. I'll speed it up a little bit. So as it's speeding up, you can begin to see the pattern becoming more and more clear. Let's run it a little bit faster. Crank it up. All right. And so now this is just Pascal's triangle mod 2. And so I think I was able to program up to about 4,000 before I got impatient. And the further out you go, the clearer it is. And so if you take this region, that's the same as this region and this region. And so what I hope you find interesting here is this is something I hope you've seen many times in your life. You've seen Pascal's triangle, but it's a new way of looking at an old friend. Okay, and so you can see the new triangles getting born. My kids always loved it when a new giant triangle emerged. It's actually just calling in the file from... I've already loaded in the file, but it's just having issues graphing it. Oh, it reset to 0. So I'll stop it in a moment. Or I'll just jump to close to the end. Okay, so this is close to how far I was able to get it to go. And so, again, beautiful structure in terms of what's going on here. And so the key thing in fractal geometry is this remarkable self-similarity. Okay? Now the question is, how do we plot this? This is a class on efficiency. Is it easy or hard to calculate these columns for Pascal's triangle?
Easy.
Easy. How would you calculate this dot? Or this dot? Or this dot? What would you do?
The 2 dots on the left side.
That's one way. What's another way? Binomial coefficients. Right? So in some sense, it's trivial to create these pictures. I just have to calculate binomial coefficients. Well, calculating binomial coefficients is expensive. So would I want to use the relationship that each dot can be obtained from the 2 previous? What's the problem with something like that? Memory. So now you need to keep the previous. Well, how much of the previous do I need to keep?
This row or column.
Just the previous row or column. So in terms of trying to do a calculation like this, one possibility is to just keep the previous in memory and then use that to compute the next column, then delete the previous and replace that with the one you've just calculated and keep marching down. Then, of course, there's also questions about how would you store something like this. I found it was much better to just store the cells that are alive. But of course, if you know a structure like this, do I really need to store this cell? Yes?
Well, since it's self-similar, you can basically just calculate one of the self-similar copies and then reproduce it and then just sort of calculate where it's going to be reproduced.
Yes.
And
So
copy it everywhere else.
So I could copy it everywhere else, and then if I only want to truncate it, I would have to truncate it. So the question is, how would you write code to do that well? So if somebody wants to do this, I want to use this when I teach Calc 3 in the spring. I'd like to have a really good movie of this, going pretty far down and seeing this emerge. I scoured YouTube and I wasn't able to find a good video of Pascal's triangle mod2 being born. But there's a lot of really good computational issues as to how do we do this efficiently. So we could write down a function. I can relate the value of this point to a value of a point in here, and then that point here is related to a point here, and I can keep propagating. The question becomes, how involved is it to write down that function? So there are times when it's easier not to use the specific formula because it's such a pain to write down that specific formula. But it seems very wasteful, at this level to be computing here and then all the way here and all the way here. So what can I do to save? How can I speed up this calculation? What's the fastest way to do something like this? Now again, doing this is requiring me to keep a lot of things in memory. I have to keep the entire previous row or column. That's not so bad if I'm only at 1,000 levels, but at 10,000, 100,000 levels, that's pretty memory intense. Is there a way you can do this and construct the columns without keeping anything in memory? How could we do it without keeping things in memory? So I sadly need the blackboard now for this, so I'm going to switch that off. Alright, so we're going to assume now that memory is expensive. How can I calculate Pascal's triangle efficiently without having to make too much demands on memory? And again, calculating n choose k, n factorial over k factorial, n minus k factorial, this is expensive if n is big and k